think. Sorry about this loud sound in here. Anyway, good morning, and today is the session before last because I was planning on one more session next week to talk about basically the remainder of the course. Today we're going to talk mainly about this week and especially about the assignments that are coming. And hopefully people will have questions later on, and so that they can ask them. And there is a discussion board for that too that's going to be posted on this week. Actually, it's already posted. Everything is posted up until this point. Weeks 5 and 6, they will not be available until Sunday because there is quite a bit of work this week. And I don't want them to be made available because if we do that, things will basically be colliding with one another, and there will be too much things to do. So they will be available next week, and actually week 6, the last week of this class, because it's a summer session, will be mainly focused actually on the final. There will be 2 other items due that week, namely the fact that quiz for the last chapter, which is chapter 12. And also the assignment that we have had from almost the beginning of the course, namely the lunar observation, also will be due that week. Other than that, there will be no discussion for chapter 6, basically. Unless you guys have questions, which I hope that you can ask all the time, then we will open a discussion. But again, it's not going to be graded, so it's not like the other discussions. So there is always room for communications, no matter what time it is of the course. You can always, you're welcome to ask questions. You're welcome to basically, whether it's on a one-to-one basis or on a class level, basically, where we can talk about things and clarify things, especially in terms of assignments and things like that. So that's basically in a nutshell, basically, of the remainder of the course. We are midway actually right now, and we still have the other half, which is a little bit more to go. This week is a little bit heavy, I understand that, and actually next week is a little bit more work. So I really want you guys to be focused for the next 2 weeks. And I promise after that, things will be a lot less intense in terms of work, and in terms of basically it's going to be a little bit easier down the road. The last week, once you do the review, once you complete it, you should not have difficulty with the final exam. So that's basically in a nutshell how this is working. Somebody is moving the mouse, and since I'm sharing the screen, apparently the mouse is moving in there. Anyway, the way this course was structured to begin with, and hopefully it's clearer now to you guys, is that this is for the system, and it was divided into 2 halves. The first half was just basically completed, and the first half dealt really mainly with the general approach to astronomy. What do we know? How do we know to know what we know, basically, the method of astronomy, the science of astronomy, the science behind all of the things that we know about astronomy. Because how can we be confident if somebody comes and tell me such and such planet exists, or a star which is light years away from here has this much composition or this structure and has this planet next to it and that planet next to it? And it's in a nutshell basically the laws that we learned up to now. Kepler's laws, the laws of electricity and magnetism that led to the basically the optics, namely the how we can see things, how we can analyze them, how we can do spectral analysis basically of the light that comes to us. All of this is a very important and powerful tools that we do. We don't rely anymore on just basically visual observation. Objects are far away for us to make any sense of them. So things are too far basically to be seen. Even with the most powerful telescopes out there, it's very difficult, if not impossible, to see everything in here in the universe. So we rely on other techniques, and that's basically the whole purpose of the chapters from 1 through 6, actually, the whole thing. There was in the beginning a little bit of history, and how we came to know what we know, also in terms of how the ideas evolved over time. And the fact that astronomy actually is usually and was always at the leading edge of science altogether. I mean, ideas that developed, started in astronomy, impacted physics, impacted chemistry, impacted even biology and other fields of science. So, and it continues to do so. It's always at the cutting edge of scientific discovery. So that's basically some of the things that we also take from this. We talked also about how the difference between astrology and astronomy, and the fact that one of them is not science actually, and cannot be really relied on in trying to make scientific arguments, and it's more of a psychology and sociology than science. And even then, it's not really relying on the scientific, or at least the methods of psychology and psychiatry. So it's not really a science or anything that can be taken seriously. And the other one is more serious, of course. It uses actually scientific methods, and uses things that were developed in basically based on observation and then tested and proven and things like that. So that's one of the things that we discovered in the beginning. And of course, we started developing those ideas based on observations in terms of the laws of Kepler. And the laws of Kepler basically are three laws. The first law that says basically that upon looking at the basically the objects that Tycho Brahe looked at, he was able to conclude that these planets actually orbit the sun in not circular paths as we thought in the beginning they should, but actually in elliptical paths. Then we discovered that they sweep equal areas at equal times, which means that, and it's very critical, and I know it was one of the questions in the homework, and some of you probably didn't catch on it, is that, look, if it travels shorter distance near the star and travels a further distance away from the star, from the sun, so it must travel, since it takes the same amount of time, so basically it must travel at different rates, and that is the thing that needs to be taken from there. So the speed is not constant. Unless it's really a perfect circular path where the distance is the same, then the speed will be the same. So other than that, the speed is not the same. Obviously, the velocity vector, which is different than the speed, is always changing because of its direction. So those are some of the things that's coming from the second law. The third law basically gives me quantitative measurements, basically how to actually, based on night after night after night, observing an object and how it changes in the sky, I can determine its angular speed. And based on that, I can actually determine its period, how long it's going to take to come back into the same position again. Now, knowing its period, how long it takes to go once around the star, around the sun, then I can determine how far it is from the sun. And that is a very powerful statement, because that was used for a lot of other observations. And then if I know how far it is from the star and how fast it's moving, I can actually determine the mass of the star. So this is one of the ways to measure the mass of the sun, without actually having to weigh the sun, without having actually to take the sun and put it on a scale. There is no scale in the solar system or anywhere actually that can fit a single planet, let alone a whole star. But that's basically one of the things. It's based on these laws that we can measure things. Because one of the things that somebody comes and you, how do you know that the mass of the sun is what, the mass of the earth is 6 times 10 to the power 24 kilograms. Did anybody go and weigh the sun and put it on a scale? No. So this is some of the things. Just by looking at the moon and determining its period, we can determine that based on Kepler's laws. So that's really powerful stuff. Then, of course, we discovered Newton's laws and how they were helpful in giving us an extended version of Kepler's laws, and actually going beyond what Mr. Kepler has discovered. So that's basically, and giving us predictions, because later on when Mr. Galileo, for example, observed the moons of Jupiter, we were able to use the modified version or the improved version of Kepler's laws based on Newton's theory and measure the mass of Jupiter. So that's some of the things. Not only that, we used actually Kepler's laws, Newton's version of Kepler's laws, to actually predict, for example, when that comet will come back. So that's really some of the things that we have discovered in there. So this is in a nutshell. And then, of course, we went to Maxwell's theory of light, which was also enabled us to discover some of its properties, which is the wave nature, and how that is actually very helpful for us. We went a step further actually than that. We discovered that light on the atomic level is due to the transition of the electrons from one energy level to the next energy level. And based on that, we determined that every single atom, every single molecule has a signature. And that is this jump of the electrons from one level to the other. If they were at a higher energy level and they go down, that is an emission spectrum. If they were from the lower level to and they want to jump to a higher level, that is actually an absorption spectrum. Every single element in the universe has its own signature. So if I take the spectral line, for example, and I see 1 line, 2, 3, 4, I know specifically what that element is. So I can determine the composition of objects in the sky without actually having to go to any star. And we have never been to any star other than the sun, where we sent probes next to it, actually not even inside of it. So that's one thing. So we can determine its composition. Furthermore, light has another peculiar behavior, which is the fact that if an object is emitting light and moving away from us, its spectrum shifts toward the red. And if the object is actually coming towards us, its spectral lines basically will shift toward the blue. Based on that, we can determine the speed of the object with which it's moving. If it's spinning, we can determine one side is coming towards us and the other side is going away from us. Theoretically, we should be able to determine how fast it's moving, because we can tell how fast it's moving towards us and how fast it's moving away from us. And that is a Doppler effect. So combining the lights of theory from Maxwell and also the quantum mechanics version of light, we add to it the Doppler effect. We have a lot of powerful stuff. We can know the composition, we can determine the speeds, and that's how actually later on, when you take Astronomy 1B, if you're going to take it, you will learn actually how the universe is expanding and how we discovered that based on the light of theory. You see, this is in a nutshell what we have discovered in here, and that's really a very powerful basis for which you can continue your astronomy studies and actually other subjects of science if you're interested. So if tomorrow you're reading a paper and it says astronomers have discovered a planet near a star, and this is what they have found, or discovered an object that is coming toward the solar system, and this occurs all the time basically, then you can learn. Like for example, today, or at least this week, we're looking at this newly discovered comet that everybody is looking at the sky, and today is the 14th, in 2 days from today, on Thursday actually, it's going to be very close from the Earth, as close as it can go, as close as it can be, which is 0.69 astronomical units. I mean, it's still far, but it's visible. It's very visible. You can go in the morning around 4 o'clock in the morning or in the evening and look at the north. I think now it's probably moving toward the south eastern skies, where you can see it, and with the naked eye or with the binoculars you can see something, you can see more details. So this is a comet that is called New Wise, and this is things that are happening all the time, and we learn about them again based on the things that we discovered in here. So this is in a nutshell chapters 1 through 6. And hopefully you guys have enjoyed them as much as I did. I always enjoy talking about them because they serve foundation not just for this field of astronomy, but also for other fields. If you're reading a paper, for example, on even medicine, for example, and how they use optical devices, for example, X-ray radiation or other devices to do studies, for example, of whatever they are trying to discover and do, you have a better appreciation now. You know exactly what an X-ray radiation is and how it's, at least the foundation of it is. So you should be able to at least what people are talking about. So that's in a nutshell what we did so far, and it has more implications in other fields than astronomy. The second half, though, deals specifically with the solar system. We're going to be looking at the solar system in detail. We're going to talk about the planets in the solar system, and then into two major groups. The first group is the Earth-bound, basically Earth-like planets, and they are Mercury, Venus, Earth, and Mars. And they are all rocky planets, as we will discover, and they are all basically warmer planets than the next four. So the solar system has 8 planets. And the 4 that come after that are, of course, the giants. And they're super big, starting with the biggest of them all, Jupiter, and then followed by Saturn, and then Uranus, and then Neptune. And that's basically the planets of the solar system. There is a line between Mars and Jupiter that separates the 2 kinds of planets, and that is the frost line, beyond which water basically can only be in solid form, namely ice, and below which water can have different forms. Basically, it can be both in liquid and gas and solid form as ice. So basically, that is the frost line that determines the separation between the 2 objects. And then there are smaller objects which are actually too many. The first kind of objects are dwarf planets, and dwarf planets are too many also. They're actually far more than actually the planets themselves, and we continually discover new ones. Most of them reside beyond Pluto, Neptune, and they are called PNOs. Basically, Pluto, what is it? Anyway, objects that are beyond Neptune, basically, and they are in the Kuiper belt, actually, and they're the biggest one, or at least the most well-known of them, is not the biggest by far, is Pluto, but there is also Eris, and there is also so many of them in that region. Okay, and they're all dwarf planets, and then we have one of the dwarf planets that actually exists inside the between Jupiter and Mars, and that's part of actually the asteroid belt, and that is actually Ceres. So that's, in a nutshell, some of the objects that are in the solar system as a form of dwarf planets. Dwarf planets are still planets, but they don't have a lot of mass to do what normal planets do, and namely to sweep their region. And that is actually a debate thing that was that you probably heard of, and to how Pluto was demoted from the rank of a planet to a dwarf planet, because we discovered so many Pluto-like basically objects, and that's why we came up with new classification. Now, dwarf planets are not in any sense less important than planets, and actually some of them have moons. As a matter of fact, Pluto has more moons than any of the inner planets. It has about 5 moons, so it's a big object in terms of, it's a system by itself. Earth has 1 moon, Mars has 2 tiny moons, which are captured basically objects, and Venus and Mercury have no moons. So that's basically some of the features that some of them actually have rings too. So dwarf planets are a complicated system, and they have all kinds of features that are important by themselves. Finally, you have the ring structures, which is by itself is another one of the. No, I'm sorry. Before that, there is the moons themselves. The moons can be complicated, and they have a lot of their features themselves. And as a matter of fact, the new studies actually suggest that some of the moons near Jupiter, they could be host to life as we know it, carbon-based life. So, which suggests, because they have water in the liquid form, and which could suggest that if we're looking at exoplanets and we're trying to look for life outside of the solar system, we may find it probably more likely on a moon than on a planet. So that's one of the things that is important about the moon. There are too many moons. Jupiter has about 70 moons. Any of the objects outside of basically beyond Mars has moons, a lot of them. And some of these moons are big. Callisto, Ganymede are big moons. And then you have also Titan, which is the moon of Saturn, which is also a super big moon. In addition to a very odd object in the solar system that really stands out because of its location, and it's because of its size, namely the fact our moon, the Earth's moon, is too big to exist inside the, compared to at least the other planets in the inner system. They don't have a moon, and if they do, it's very tiny rocks. So, but the Earth has, it's kind of an odd object to have this big moon. In terms of ratio, planet to moon, actually the biggest ratio falls to Pluto. Pluto's moon, Charon, is relatively speaking, the biggest object ratio, at least in terms of moon to planet, than anything in the solar system. So these are some of the oddities about the solar system in terms of moons. Then, of course, like I said, there is the ring systems, which is a complicated structure around some of the planets. All of the outer planets have rings, including Jupiter, Saturn, of course, which is the obvious one, Uranus, and also Neptune. So they all have ring systems around them. And then there are other objects, basically billions of them to count there in the Kuiper belt, and then actually beyond the Kuiper belt in the Oort cloud. So this is in a nutshell the solar system. So let me give you a visual of how the solar system goes. I know we have a project, and I hope to not forget to talk about, and I'm sorry, an assignment, not a project, as a homework basically, namely the Stellarium project. But I want to share with you another software that actually I have, and that is actually simulation, not real, not like Stellarium. Stellarium is actually what you see if you go outside tonight and look at the sky. So that's basically what you will see. Or if you have powerful telescope that you can basically use, and with filters, what you can see during daytime, especially if there is a solar eclipse or something. So let me share with you the other software, which is really, like I said, a simulation. This is not it's not like the Stellarium. This is called Universe Sandbox. I don't know if you guys see it in here or not. And this is actually can be an animated. It actually, by default, it's animated, but I'd like to pause what I'm looking at right now. Again, when you go to the sandbox, you can pull objects from it, whatever you want to study. Right now, I'm looking at the solar system, and you can simulate all kinds of things. For example, you can simulate, let me go back in here, close this. You can simulate basically collision of planets. What you see behind me in the animation behind me is actually was generated by this software. And what I did actually, I took all the 4 objects in the solar system outside of Mars, namely Jupiter, as you can see in the picture. And then I took Saturn, Uranus, and Neptune, and put them one next to one another, actually put them very close to one another. And I added to them the hypothetical planet 9, which is another object, another topic for another by itself. As you can see them, and I put them very close from one another. And then when the animation starts, I did not start yet, you will see that there is collision between these objects and they start falling on one another. And because even Saturn, that is very big in here, will actually collide with it. And what remains in here is planet 9 because it's supposed to be a big planet, but even that is going to collide in here. Again, you can simulate a lot of things with this software. And if you want to have fun, you can get it. And it's really not that expensive. It's about $30 if you can afford $30. Actually, for students, I think it's about $20. So you can acquire it. It's a Universe Sandbox. You need a little bit of a powerful graphic card, though, because this is intensive in terms of graphics. And it goes way beyond the solar system. Actually, you can look at galaxies, you can look at stars, you can simulate all kinds of things. And you can take, for example, Betelgeuse, and you put it next to the sun, and you will see how big they are and what happened to the sun in that case. And you can take big, super big stars with small dwarf stars, and you can do simulations like that. But that's not the point in here. What I'm looking in here is the solar system. Since I have zoomed in here on the sun, can I close this thing in here? Let me move this object out of the way. So when I have the sun centered right now, I'm looking at its properties. And one of the properties that I really want you to pay attention from now on to the rest of this basically course is the density of an object. The density of an object tells me basically a lot about its structure. What is it made up of? For example, the density is about 1.4 grams per cubic centimeters. The water, which is a base with which we compare things, is 1 gram per cubic centimeter. So this is slightly more dense than the water. So if I take the sun and put it in an ocean, and there is no ocean that we know of that can fit the sun, it's going to sink. So that's because its density is a little higher than that of water. But that's not really the reason why we look at the density. The reason is because it tells me more about its structure. That means it's mainly gas and probably with a dense core. So that's basically what this is. As a matter of fact, if I go to the composition, it tells me what is it made up of, and it's looking at the iron and hydrogen. It's basically about 100% hydrogen. As a matter of fact, it's less than that. So don't take these numbers in here exactly, because we know the sun is not, and we'll talk about this one, is not a first generation star. It's actually a star that came after other stars that existed in our neighborhood. How do we know that? Well, for example, if I take any object in here, doesn't matter, Venus, for example, and look at its structure, it has iron, and iron cannot be produced in a first generation star. It has to be with the, I mean, it cannot exist in a first generation, basically, solar system, because it's coming from big events in the universe, namely, for example, something that you will learn later on, which is supernovas. So that's Venus. So it's telling me about its composition. It has 20% of iron. And again, since I'm looking in here, I'd like to know about the density of this object. The density of Venus is 5.24 grams per cubic centimeter. That means it's made up of a lot of rock and silicate, namely, and also iron and metals inside of it. That makes it more dense. Then if I compare it, for example, with Saturn, if I look at Saturn, its density is 687 kilograms per cubic centimeter. Remember the per cubic meter, actually. Remember the unit for Venus was grams per cubic centimeter. And now, since we're dealing with Saturn, it gave me a different system. Oops, let me go back to the sun. I don't want to be near, I don't want this system to be centered on. So Venus is 0.68. I have to divide this by 1,000 if I want to convert it to grams per cubic centimeters. Or I can change back to the unit in here. It's 0.687 grams. So it's less than water. That's an interesting property. So if I take Saturn and put it in an ocean that can fit it somehow, Saturn will sink. That's one of its properties. So this is one of the properties that I want you to really pay close attention to, namely its density, because it tells me a lot about basically its structure. The solar system, as you can see from this one in here, this is not the entire solar system, by the way, because if I want to see where, for example, Saturn and Uranus, Saturn is here, but if I want to find where Uranus is or where Neptune is, I have to really zoom out. And you see the distance in here. Here is actually Venus. And if I want to find where Mercury is, I have to come very close in here because, again, the inner planets are very close from the sun, actually, although we see that the Earth, for example, is 150 million kilometers, but it's very close from it. So we have the objects. Again, we have Mercury, Venus, Earth, and then we have Mars. Between Mars and Jupiter, if I can find where Jupiter is, here is Jupiter. See, there is a big distance, first of all. The distance between the Earth and the sun is, because it's 150 million kilometers, we converted that into astronomical units. We call it 1 AU, 1 astronomical units. The distance between the sun and Jupiter, again, let me go back into the sun. Where is Jupiter again? It's the distance to the closest star is 5 astronomical units, basically. So that means that the distance between the Earth and Jupiter is about 4 astronomical units. As a matter of fact, it varies between 4 and 6. One of the things that you can do with Stellarium is actually go and see the object and how much, change the date from today until a year from today, and you will see the distance between Jupiter and the sun changing accordingly, and actually the distance between us and actually the sun and Jupiter also changing in a year, because it's not the same distance. At some points it's closer by and the sun on the other side, and the other time it's further away because there is a 5 AU plus 1, so it puts it at 6. So between these two, there is all kinds of smaller objects that you can see in here. The biggest one of them is Ceres. Ceres is a dwarf planet, I'm sorry, and it's inside the so-called asteroid belt. There are millions of objects in here, in this region. They're very tiny, very rocky, very small of them, but there are too many, and they exist between Jupiter and Mars. Okay, so that's basically the path of them. So the biggest object, which looks spherical in here, actually you can see the object in here, that's Ceres, and its density, again, since I told you to pay attention to that number, it's 2.16 grams per cubic centimeter. So it's not as dense as planets, like for example Mars. Mars densities is actually almost 4 grams per cubic centimeter. So it seems like it has less iron and less metals, for example, than Venus, which was a little over 5. And as a matter of fact, if I can find where Mercury is the second most dense object in the solar system. Its core is mainly basically metals. And as a matter of fact, there was a paper that came out in this year that argued that actually this planet was a giant gas planet, and it lost all of its gas, and now basically that's what its core is. And there was an argument based on that paper. But the most dense object in the solar system is the Earth. 5.51 grams per cubic centimeters. Earth is the densest object in the solar system. So if there is anything that the solar system the Earth has different than everybody else, it's density. Then of course we have Saturn. And now let me zoom out to find where Uranus is. Here is Uranus. Look at the solar system now from a distance of the Uranus is and Neptune is. It's very, very, very dense. I mean, even Jupiter seems to be very close from the sun. And that is because we are at very, very high distances now. We are at 20 astronomical units compared from the sun. That's for Uranus. And now if we look at Neptune, Neptune is about 30 astronomical units. And if I can find where Pluto is, that's about 40 astronomical units. Right now it's about 32, but usually because its path takes it sometimes inside of the path of Neptune, and because it's very elliptical, so on average it's about 40 basically astronomical units from the sun. So that's, sometimes it takes it inside Neptune, and sometimes takes it outside of Neptune. So that's basically, I mean, the object, I'm sorry, I just remember, it's not PNO, it's TNOs, trans-Neptunian objects. I just remember the word in here. Sometimes it's a trans-Neptunian object, and sometimes it's below Neptune. But most of the other objects in here, outside of this one, and they are actually far, far away from it. We have Haumea in here. We have Makemake in here. Those are all dwarf planets, by the way. We have other ones that are famous in here. Where is the other one? Yeah, Eris. I'm trying to find where Eris is. Actually, there are more objects in here. Here is Sedna. Look, from the distance of Sedna, even Neptune becomes very close from the sun. And that's actually another dwarf planet in here. And I'm trying to find, oops, more objects. By this time in here, we are almost in the Oort cloud, which is the outer limits of the solar system, basically. So this is in a nutshell an overview of the solar system. Of course, let me zoom into the sun again. So by this distance in here, this is basically what we usually talk about when we talk about the solar system in here. Okay, so this is the perception that we have. One of the activities we do usually in class is to actually build a model for the solar system to see how big objects are in terms of distance and in terms of how things are located and things like that. So this is an overview basically of the solar system, of how things are. And then of course we delved into details in the next chapters, for example, into Earth. Let me try to zoom in onto Earth a little bit. and try to find its moon. At this point, we're not seeing the moon, okay? We're still far away from it. I'm trying to find where the moon is. Is it not visible in this case in here? Obviously, probably we'll need to. Okay, one of the things, if you're gonna find these things in here, you probably have to turn on some features and turn off some other features. And for some reason, I don't see the moon in here, probably because it's not added. So let me exit this software and go to the more realistic one to do comparisons, okay? Because this is actually simulation. It gives me an overview of things. Let me exit from here. Exit, yes. And let me go and find the other one, because the other one actually is a little bit more. Okay, here is the Stellarium. And let me find where the moon is. Again, I'm looking from my current location, which is really in Loma Linda right now. And let me turn off some of these features. I don't know why I have an object selected in here. I don't want to have anything selected. Okay, no matter what, it seems like I have something selected. Anyway, let me find the moon. Okay, the project in a nutshell is for you to, okay, here is the moon now. It gives you even the phase of the moon right now. Okay, that's interesting. And the moon, as you can tell, and probably you have looked at it with your own eyes, you don't even have binoculars or anything like that to look at it, has a structure that has all of this basically craters on its surface. And it's critical from this, at least the next chapter or so, that you focus on these ideas in here. First of all, on this side of the moon, it seems like it has those, what people initially thought that they were oceans. They gave them names of mareas, basically, which is, I think, I don't know where it's coming from, Latin probably, but I know the word in French means basically le mare, which is like lakes or like surface water or something like that. So, but they are not. They're actually remnants of overflow, basically, from lava that when the moon probably was hit initially, and then basically all of this volcanic activities during the early stages of the formation. So those are the liquid that formed in there. They're not water, but they're lava, and that's basically the remnants of it. So that's basically the dark surfaces, and versus the higher levels of the moon, which are more reflective of the light. And basically, that's basically the structure of the moon. But then there is these craters, with they're so small and big, and that enabled us to have an understanding, basically, of how we can use that, because we can use that to do a lot of things. One of them is to tell the age of the surface of a given planet if we know, or if we count the craters on it. So that's a very powerful technique to determining the age. Again, there are two techniques, and you'll have to go in detail in the book about them to determine the age, basically, at least these two, namely craters, and there is also that determines, tells me basically the geological activity. If I see a lot of craters, I would say that this surface is old in terms, it's not doing a lot of geological activity, because if it has less craters, then there is a lot of activity on its surface. So that's basically what's going on. Now, the other technique is, of course, dating using radioactive materials. And this is another property that we can use, depending on what we're shooting for. For example, in the case of the planets and rocks, they're in the millions, sometimes in the billions of years old. So we have to use radioactive materials that have a half-life that is of that order of magnitude. So if we know, for example, that specific element can live for so many years before half of it is gone, and if I can determine the proportion of it and its isotope that it, or at least the element that it transformed to, I can use that backward to determine the age of that rock, basically, and determine its age. So those are some of the things that you need to pay attention to. So when you're reading about this one in here, especially, for example, in terms of the moon, and let me find another object in here that I can, I think, let me turn off no, I don't want to turn on this one in here, because if I turn on this one, it's daytime right now, so I probably have to move it at night. Another item that you need to focus on is actually the magnitude. And I know I mentioned this one is how bright the object is. For the moon, it's super bright. -10 is super bright. Can only be matched with the sun, which is -26 or something like that, which is even brighter than the moon. Let me try to find where Mercury is. Okay, let me try to zoom on it. Again, it has phases in here because of its position in the sun in here. If I move okay, there are better pictures than this one from the course in here. Let me see if I can find them. Did I turn off? What I'm trying to argue in here is basically the surface of these objects. Okay, I think this will work. Let me stop sharing that screen and share with you quickly the screen here. So again, these are two pictures of the moon from the other side, basically, of the moon, because one of the things that you will learn actually from this chapter is that, I think we talked about it before too, is the fact that the moon takes the same time it goes once around, it acts as much as it goes around the Earth. Hence, it's giving us the same phase all the time. It's tidally locked with the Earth, and that is a very big concept because an object like the moon and the Earth, they're pulling on each other. So if the moon was moving any faster, it's going to be slowed down by this effect, this exchange of energy, and actually moved away in this case, and they will be tidally locked. If it was going any smaller, again, it's going to pick up speed just to be tidally locked with it. So that's basically one of the things. This process takes energy from the two systems, especially from the biggest one, namely the Earth, and overall, the Earth will lose energy overall, and it's actually going to slow down because of this effect. So the day in the past was a little shorter than what it is today. So that's one of the things that is going to come from this one. And the biggest thing that I want you to look at is the number of craters in here. And that enabled us to come up with an idea, basically, an understanding and a plan for the solar system, trying to learn from it and use that as a measure to determine the age of other objects, if we can count the craters on its surface. Again, that is basically the metric that we use in here. This is the graph that we use in here. So cratering rates over time. So that studies, intensive studies enable this to do that. So if we look at the surface of, again, Mercury, it's the same thing. It's also heavily cratered. So whatever happened to Mercury happened early on. After that, it was bombarded with the same method that the moon was. So that's one of the things that basically you can conclude from that. So again, there is a heavy bombardment by the by objects from the solar system falling on it, and then after that subsided. It did not go completely out, so still have an ongoing basically impacts coming toward all of the solar system objects, including the Earth, which is at some point will undergo such a behavior. So that's one of the things that I want you to pick up from this chapters. Of course, we have other topics that we can talk about, namely the fact that the surface of the Earth has its own specific geological activities that changes its form, and that's why we don't see as many craters in here. We have volcanoes, we have earthquakes, we have basically plate tectonics, which is actually the drift of the continents, but also we have the atmosphere, which plays a major role in terms of the number of impacts. You have to have a big object that can penetrate the atmosphere and actually make an impact on the Earth. Otherwise, it's going to be basically decimated in the atmosphere. Which takes me to the case of Venus. Venus actually has a thicker atmosphere than the Earth, so there should be less craters on its surface. You need to have a big object to really penetrate that thick atmosphere and go to the surface of the planet. So in terms of that, and also if we look at the surface of Mars, for example, it has more craters than the Earth and Venus does, but it has less craters than the case of Mercury and the Moon is, because at some point it had actually atmosphere. So that's the difference between the two. And actually it has the geology also that changed it. But if you look at the surface there, you will see some geological features. Of them there are craters, and sometimes it's the other way around. So you can determine which one occurred first, basically, and you can determine the age of this phenomenon there. For the case of the outer planets, they have super thick atmospheres, and we don't even know, we are not even sure if they have a rocky structure in the bottom. As a matter of fact, they probably don't, because if they do, it's really actually gas, liquid hydrogen, or even compressed further hydrogen states that we don't even understand at this point. So that's basically the difference between these objects. Their gravity is too big, it's going to attract anything to them, and before they even impact the atmosphere, they probably are going to be exploding. So that's really what the difference between these objects. The surface of the Moon is very dusty because of these permanent collisions. Each collision will bring more dust to the surface, and that's why, if you look at it, that's basically what this, when the astronomers were moving on its surface, that's basically what they experienced. Other than Earth, the only object we were able to visit was actually the Moon. So that's with man-made, basically, one man, person going there. Our technology went to other objects, especially Mars. We have a lot of visits for Mars. We had a lander on Venus, but did not survive there for a long time. We actually orbited also Mercury, and we did mapping for its surface. And we did a lot of these studies, at least for the inner object. For the outer objects, we did do some orbiters, a lot of orbiters actually. But we had actually landers on actually one moon, namely the moon Titan from Saturn. We never landed on anything else. And that's the... we studied their surface, we had orbiters, we basically, and then at the end, the Cassini project, instead of going completely, basically, we directed towards Saturn in 2017, and basically it exploded on the surface, collecting a lot of data that we're still analyzing from that experiment, basically observations. So basically this is, again, we're talking about the introduction of the solar system, which I just did. We talk about the Earth as a planet, and that is a key thing in here that we have to understand. The fact that the Earth itself serves as a model for us to study other planets. Basically, if we look at the surface of the Earth, it has a lot of weathering. It has a lot of basically the atmosphere itself is moving, and it's giving us a lot of basically changing to the surface, to its surface. We have the plate tectonic. We have actually its structure also that we can determine using seismic studies. Basically, we send waves, or at least when earthquake hits or something like that, we collect the data, and based on that, because waves reflect differently at different surfaces with different densities, we can determine the structure of the inner planet. We didn't do that with anything else other than the Earth, so that's why we have a full understanding of how Earth, in terms of its structure, is. Now we're doing that with Saturn. We had actually a lander, what is it, last year? Yeah, we had a lander in 2018, and now we're collecting Martian quakes basically on a regular basis, and trying to study basically the structure of Mars using the same techniques. We didn't do it with any other object, so that's one of the things that we learn about the structure of the other objects. One of the advantages of the Earth having this core in its structure, which is metallic, because metal, when it's hot, it has free electrons basically, and when it's spinning, these electrons will move. In doing so, you have a current, basically. That's what the current is. It's motion of charges. So these charges are moving, creating currents, and a current moving creates a magnetism. This is one of the consequences of Maxwell's equations. So you have that current that creates a magnetic field, and that magnetic field serves as a shield on Earth in here. It's a very critical shield in here. Without it, we will be bombarded by the solar wind, which is heavily, super fast particles that can destroy any life form that exists on the Earth. So without this magnetism, Earth could not be, would be hostile to life, basically. It would not be welcoming to life. So that's a critical piece in here. So that's something that is very important for us to understand too. Mars does not have it's spinning fast. It's spinning the day on Mars is 24 hours. So it's exactly, slightly actually longer than the day on Earth, few minutes. But that's still super fast moving. But it doesn't have a molten core as the Earth does. And so basically it lost its magnetic field, at least very, very small, if anything at all. So it's not protected from the solar wind or the cosmic rays. So that's one of the things that are beneficial to Earth. Venus, on the other hand, moves extremely slow around its axis. Takes almost 6 months, half a year for it to complete one day. So it's very, very slow. It's even worse in the case of Mercury. Mercury moves even slower. Its day is faster than it takes longer for its day than its year. So by the time it goes 24 hours, basically a whole day, it has completed a whole year around the sun and more. So that's one of the things that is unique to Earth, and we're protected. Obviously, when we talk about the giants, the big giants, they have far more magnetic field than the Earth does, especially in the case of Jupiter. Far more powerful than the Earth, and actually it's one of the most, the biggest features in the solar system is the magnetic field of Jupiter. But then it's also not good, because if we're trying to probe those planets, those magnetic fields are too powerful, and they could be damaging to our probes. And actually that's one of the problems that Galileo, the mission to Jupiter experienced and had to deal with, was the magnetic field of Jupiter. So that's basically the crust itself of the Earth is always regenerated, and it's always changing because of the heat that is coming from the inside of the Earth. And the heat has two sources. One of them is the remnants from when the Earth basically cooled and formed. And the other one is actually coming from radioactive materials that are inside the Earth. That's one of the problems that Mars did experience, namely it did not have a lot of, it was smaller to begin with, so whatever heat it had in the beginning was not much, number one. Number two, since its mass is less than the Earth, it does not have as much radioactive materials as the Earth does. So it's cooled down quickly and basically lost all of its magnetism and lost all of its atmosphere, and basically is the barren world that we can see right now. Unlike Venus, which has almost similar mass like the Earth, so it has the same amount of heat, almost the same amount. It's less, but it's almost the same amount of heat as the Earth does, and some actually, because something weird happened to Venus about 150 million to about 600 million years ago, in that it lost all of its basically carbon dioxide to the atmosphere and became a hellish world as we can see here today, because basically the oceans boiled, and after that, if it had life, that life basically could not have stayed on its surface. At best right now, we speculate, if it exists at all, it's probably somewhere airborne in its atmosphere, because there are so many components in Venus that are not good. So this is some of the things that we know about the Earth. One of the things that we need to focus on is the atmosphere. Again, the atmosphere, the temperature is not fixed, the temperature is changing, and the atmosphere adds another feature in here on Earth. It has this ionosphere, and it has the ozone layer, which protects the life on Earth, because the ozone layer has a big feature. It interacts with the ozone itself, which is oxygen-3, interacts with the incoming basically ultraviolet radiation and changes its structure. In doing so, it absorbs basically the UV radiation. Without it, again, life will be exposed to the radiation, and that's also not good. One of the things that they are thinking they need to do to COVID in here is to expose it to basically radiation to kill it. And UV radiation will kill any life form on the surface of the planet. So, which is another problem in here, because let me go to this graph in here. one of the things that is not politics, and I know we're politicizing everything now from face masks to whatever there is out there. This is not politics. This is real science, and we have to really be careful with that. As much as we try to argue against our, astrology, this is also something. This is not a myth. A human activity leads to more carbon dioxide, which really creates an imbalance in the system and raises the temperature in the Earth, and then causes basically greenhouse effect, which is going to have detrimental effects on life on Earth, not only in terms of the UV radiation, because those gases released will destroy the ozone layer and exposes life, but also increases the temperature and makes life impossible on the Earth. The greenhouse effect is basically the radiation that just penetrates the atmosphere has different wavelength, from long to short. The Earth absorbs that radiation. All the radiation is absorbed by the Earth. The Earth warms up because of that, that radiation. Now, when the Earth warms up, it's going to emit radiation in the infrared. That is basically when you heat up an object, it's going to radiate. An object that is heated up will emit heat. And that heat is infrared, really. And infrared does not penetrate the atmosphere. So basically, it's trapped. So it's going to be reflected back to the Earth. What it's going to heat the Earth would heat up, and it's continuously being heated up with the other radiation also. So now the temperature of the Earth will rise. It's like the phenomenon, basically. And don't try this one at home because it's very, very dangerous. If you are inside a car and you close all the windows, the temperature outside might stay, for example, 90 degrees, but the inside of the car will start to rise and rise and rise and rise until whatever is in there in terms of life form is going to basically be so hot that they can perish. And this is why some parents are very negligent, leaving their children going shopping. Even for a few minutes, they come out and then some deadly things will happen to their children, or sometimes the animals, which is even worse because those things, they cannot cry or tell you exactly what's going on with them. So this is the greenhouse effect. It's a daily thing that we can experience on Earth. All we have to do is just put, and that's basically how the purpose of the greenhouses are used to plant basically plants. So even the people who don't believe in this and they think that it's politics, they don't mind using the greenhouse in their fields to basically pump up their crops and basically produce more tomatoes and more peppers and things like that. So they use this phenomenon. So that is science, and if we're not careful enough with our life, basically, on where our atmosphere in here, it's gonna hurt us a lot. So this is not politics. It doesn't matter if you're on the right, on the left. This is science, and you have to really take it seriously. Same thing in here. This is the life, basically, the tree of life on Earth. And we always thought that probably if we go to an alien world, we'll find life and then we will be able to talk to them because we will be seeing them walking on 2 legs or 4 legs or something. But as a matter of fact, the vast majority of life in here is not of the form that we can think of. It's mainly basically other microbial forms. And that is basically the thing that we have to take into account too when we're exploring exoplanets. And even moons, for example, with inside the solar system. One of the things they were very careful with, because they know Europa has a liquid, Europa, which is one of the moons of Jupiter, has a ocean under its atmosphere. It's thick, basically, crust of ice. So they were very careful not to introduce any foreign objects and have one of our satellites fall on it. I'm sorry, one of the probes fall on it, because if it does, it might basically interfere with that life form. So again, most likely if it's there, it's in this form. So this is something in a nutshell about the Earth in here. Let me go quickly in here because I know the time is running out. The other chapter that I already briefly talked about is the creator words and the introduction of the solar system. Now, the thing that I want you to pay attention to, and it's very critical in here in terms of the assignment, is the stellarium. Okay, let me zoom back on the stellarium and go back to where I was. Okay. I'm looking at the east skies right now, and that's where the sun is right now. So this is actually a live shot. How to turn off the light is just by clicking in here, okay? So right now this is daylight time because I'm actually in the day. So if I want to change the clock, I'm just giving you an overview of this software because you will be doing this a lot. So for example, right now, today is July 14th of 2020. I can change because some of the activities is going to ask you to change the date, for example, either manually or using the up and down arrow. So I'm going to change it to October 14th. At 9 o'clock in the morning, the sun's position is in here. So if I click on the sun in here, this is the sun's position, the altitude and the azimuth and the declination, and these are the apparent measurements in here. So if these are some of the things that are going to be put in your table. So if I change it to December, for example, 14th, so it's going to be December 14th, the same time that I'm going to observe it in there, this number change. So that's what I need to be putting in my table if I'm doing Earth. Of course, if I'm looking for Arcturus, I'm going to find it in here. So I need to really find where that object is. Arcturus, it's in here. I sometimes have to spell this whole thing in here. So this is where that star is. I need to zoom out to see the whole thing in here. Again, I'm supposed to do it probably at night. So let me change the night in here to 2100. That's 9 p.m. Okay. Again, it's a military time that we're using in here. So Arcturus probably is below the horizon right now. But again, it's giving me all of the data that I need. That's one thing that I want you to be familiar with. The other thing also is, of course, we need to do the sun too on December 21st, March 21st, June 21st, and September 21st. So you need to have those dates by changing the date in here and making sure the times match as the instructions tells you, and record the coordinates in here. This is what you're going to be looking at, okay? This is RA declination, right ascension declination, and right ascension declination, and this is the apparent values, and this is basically the values that you need to be. This is the J2000, and it tells you not to use it or to use it, so you have to follow the instructions in here carefully, and then on dates and so on and so forth, okay? So these are some of the details I want you to pay attention to. One of the things that you really need to be familiar with is this bar in the bottom in here. You really need to know how to use this one. One of the things it tells you is to change from an azimuthal to equatorial and vice versa. So you need to click in here, and you will have the view change. Does this number change? That's the question basically that is asking you. And let me go back into some of the other features. Again, I've used this one in here a lot. I've used the search feature in here. This is the location, and you're supposed to do that. At some point, you're going to keep your location where you are right now on Earth, and you change the planet. So how am I going to do that? So if I go in here, you see here in the bottom, it says planet, it's Earth. Now I can do the same thing and find another planet, and it's asking you to do Mars. So let's do Mars in here. And now we are on Mars looking at the same object in here, okay? So because the coordinates on Mars did not change, so now the coordinates on Mars, the numbers in here should change slightly because we are not on Earth anymore. So I need to note those numbers in here. So let me go back to Earth, just to pay attention to those numbers in there, and they change, okay? So negative 36 degrees, for example, to, let's pick up Europa, one of the moons of Jupiter, and here, it's negative 13 degrees. Again, it should not change that much, honestly, because of the fact that we are inside the solar system, and we're looking at the star, which is Arcturus star, which is very far away. Now, if we are on this, that is the parallax that we were talking about in the lecture before. So this is some of the things that I need you to pay attention to. Now, let me stop sharing the screen because there is another part in here that is very important, and I'm going to close with it unless you guys have questions. Let me try to find the actual assignment to explain to you how you're going to do that assignment. How you're going to fill the fields in that assignment. So let me open the PDF file. Open it with Acrobat. Okay, let me share with you that screen now. So the instructions themselves are the PDF fillable file, basically. Download it first to your computer and then start filling in your information. So please do not forget to put your name, that's critical. But then a lot of this instruction says do this and this. So when you're done with that, please check the check mark in here. So that's it, that you have done it. So you earn your points in there, because if you look at the instructions, it tells you how many points you're going to earn just for doing that. So if all I have to do now is Stellarium and change the location to Riverside, California, I'm going to change the location to Riverside, California, and that's it. So just go to the location. Let me go back into that step to do just this one in here to show you how that is done. So let me stop sharing that screen and share with you this screen specifically to show you how that is done. So I'm on Stellarium again. Right now, actually, let me go to the location, which is the top arrow in here. So right now, actually, we are not on Earth, so we need to go back on Earth. And look for Riverside. So I'm going to put it says to put the first 3 letters of R-I-V and probably more. It says 5 letters, river, and probably more, side. Now, when you put the 6th letter, in this case, it narrowed down the search for me. I mean, if I put 1 letter, it's going to give me a bunch of cities with R in it. And then I have to look for Riverside, California. I'm not looking for Riversdale, South Africa. I'm not looking for Riverside, Ohio, which is another Riverside apparently in the United States, but it's in the state of Ohio. I'm looking for Riverside, California. Once I do that, that's it. Now I'm in Riverside, California. I could check on it on the bottom in here, and it tells me I am in Riverside, California. So now I know I have done that. So I go back to my report in here, my PDF file in here. Where is it? Yeah. And check that I have done that. I earned a point for that. Then I go in here, set the time, the same thing. I've been changing the time with you guys, and it's exactly under the location. Set the time, and then follow all of these instructions, basically fill the blank. Now, once you find at some point, always use the J2000 coordinate for the right ascension and the declination. Remember, it was giving me 2 coordinates, and here it's telling me use that only. So I'm looking at Polaris, so I need to find Polaris in the search. And then once I find it, then I'm supposed to just record the coordinates for it. Okay, remember I'm supposed to have used this date in here, which is July 7th, 2020, which is last week, last Tuesday, at 2100. Now, if the clock moves, you can stop it. Let me show you how you stop the clock. Let me share with you the Stellarium in here. Why it's not sharing? Okay, let me make sure that I'm sharing with you the screen, because Stellarium. Okay, so right now it says to move the clock. Let me show you how you get to it again. Just go in here under this button in here, and now it says to move the date to July 7th, which is, I'm sorry, the time is 2100, I'm sorry. It's 9 o'clock, so it's 9 o'clock. And the date actually is not the 12th of June. No, not December, I'm sorry, July. It's using a military time, which starts with the year, the month, the day, and the hour, and so on and so forth. It's coming from this down. So July 7th at 2100, and I'm going to try to put it at 0, and come in here and stop the clock. Right now, the clock is stopped. I can actually move it back to 0 if I want to. Right now, the clock is stopped. If I resume the clock will move. So now they told me to find where Polaris is. So I'm going to find Polaris. Again, I'm still in Riverside, California. I have done that. Okay. It doesn't matter, though, how it looks like. What you're looking for is this numbers in here. 2 hours, 31 minutes, 51 seconds, 51.17 seconds. That's for the right ascension. For the declination, it's positive 89 degrees, 15 minutes, arc minutes that is, and 51.4 arc seconds. Now, we think it has to be 90 degrees. Didn't we say that that's what it's supposed to be at 90 degrees? But it's off slightly because actually they don't line up exactly how it should be, but that's the number you're going to report. Okay. I hope the instructions are clear, and if you guys have any questions about them, please do ask. And I'm gonna post this recording hopefully this evening, because sometimes last time it took forever basically to upload, because I don't know what happened, but it took a long time for it to upload. And hopefully you guys finish this assignment, which is due, I believe, by the end of the week. And also you have 2 other short homework, basically assignments, which I think like 10 or 12, 14 questions, I think altogether. No, I think 10 or 11 questions each. On the average, is around that number. And that's it. That's for this week. So, and there is, I think, a quiz in between. So there is, like I said in the beginning, there is more work in this 2 weeks than any other week before and after. So it may be too much. So please let me know how we can adjust time if you're running out of time to do things, so that we can adjust things around. Okay? Do you guys have any question for me? No? Okay. Thank you for coming. And I will post this one shortly tonight, hopefully before the night is over. And if you have any questions, please do not hesitate. Thank you and stay safe.